so hi, my name's Daniel. I'm a research scientist at Google, and I'm going to talk about some work I did with you and Bo. We're going to divide the tutorial up into 3 parts. How much time do I have for the talk?
3 parts all together, 2 hours.
Okay, so like I'll do like 30 minutes. Is that okay? 30
yeah,
minutes?
I think like we'll do 30 minutes talk, and maybe you give 5 minutes Q&A for each subsection, and maybe we'll take 5 minutes break between the 3 sections. And at the end, if there are questions about all the 3 sections, feel free to jump at the end too.
Cool. Yeah.
That sound
So
good? Okay.
yeah, that sounds great. So yeah, that's super cool. Yeah. So great to talk about our work. So the work I'm going to talk about is based on so this talk is going to be based on this paper, Big SSL, exploring the frontier of large-scale semi-supervised learning for automatic speech recognition. This was a paper written by a large group of people. So my co-lecturers are both also in this paper as well. So yeah, let's start with a brief introduction and some motivation. Yeah, so semi-supervised learning refers to the utilization of unlabeled data for improving a supervised machine learning task. So it's kind of a broad catch-all term. So due to some key advancements in semi-supervised learning for speech recognition, we're at the point of being able to leverage large amounts of data, and as a result, benefit from scaling up the size of ASR models. So again, like the former is kind of more important than the latter, because if you can't really leverage large amounts of data to train your model, there's no point in making your ASR models bigger, one can argue. So in our work, we studied the effects of scaling both the dataset size and the model size up, and attempted to explore the frontier of both axes of scaling. Yeah. All right, so let's first kind of get into what we mean by semi-supervised learning. Since this is tutorial, I'll try to be kind of basic and be kind of pedagogical. So please let me know if I'm going too slow or going too fast. So the goal of semi-supervised learning is to utilize unlabeled data to improve the performance of a task that has labeled data. So semi-supervised learning, or SSL, has been especially instrumental for improving the performance of speech models, since data labeling for speech is difficult or expensive compared to other standard ML tasks. So methods for effectively utilizing unlabeled data can enable one to harness the full potential of large, deep models, because you can, in principle, access practically an infinite amount of data if you're collecting unlabeled data. There are caveats to this. There's obviously better quality unlabeled data than there's higher quality unlabeled data, of course, but like in principle, this is a much easier problem than labeling large amounts of speech. Another development that's kind of crucial, that's like kind of an important backdrop for this, is the emergence of attention-based models. So we all know that in 2017 we had these transformer models introduced into the literature, and many people actually applied these advancements to ASR models. So there's a bunch of there's a list of people that have worked on this. For now, we'll be focusing on the conformer developed by Gulati et al. By the way, if you have any questions or comments, like, please feel free to jump in and ask them. Be happy to engage. Great. So so let's try to kind of divide up semi-supervised learning into kind of like smaller into subcategories. We're principally going to concern ourselves with two different types of semi-supervised learning. One is unsupervised learning, and the other is self-supervised learning. So when we say unsupervised learning, we're referring to a semi-supervised learning method where a loss that is helpful for learning the representation of the unlabeled data is kind of designed and used to train the model. So this is training a single model essentially with unlabeled data, but you define some kind of loss that you think will be helpful to learn, quote unquote, pre-train the model with. And you just feed the model unlabeled data, and the model just learns something by optimizing that loss. So a very successful example of this is kind of the next token prediction task that's used to train language models, and this is all this has been a very successful way of training. So there have been a bunch of unsupervised learning methods developed for speech recognition. So I believe Bo and Yu's tutorials will deal with more of them. And there have been a lot of exciting developments in this direction. So the specific unsupervised learning methods. But I'm not going to talk about those. For now, we're going to stick to a very successful method that's called Wave2Vec 2.0 by Bevsky et al. So the Wave2Vec 2.0 was introduced to us in 2020, where essentially an unsupervised fill-in-the-blank task for spectrograms are used to pre-train the networks, essentially kind of like BERT, but for spectrograms. But the spectrogram representations are too dense. For example, if we try to guess a pixel of a spectrogram or a single time slice or a single feature in a given time, they're pretty easy to guess from looking at neighboring features. So some kind of compressed vector representation is made out of these spectrograms, and a contrastive loss, and then you're essentially doing kind of fill in the blank training on a fill in the blank task on this compressed vector representation. But then you're at the same time training some kind of model that's generating that compressed vector representation. So in principle, the model can cheat. For example, you can have a simple model where everything is all the vector representations of all the spectrogram features are just 0, and you have 100% accuracy in predicting filling in the blank of those features, right? So a contrastive loss is used to prevent cheating, that kind of cheating. And so what to me was most the biggest a pro of this method is that you can leverage essentially a very large data set. And even if you have a tiny amount of labeled, a small labeled data set, it can really, by leveraging the knowledge you've acquired from pre-training on a large data set, you can do very well on tiny data sets. As we'll see, we're going to talk about self-supervised methods as opposed to these unsupervised methods. And self-supervised methods tend to the returns of self-supervised methods tend to diminish as you go to as the labeled data sets get smaller and smaller. So here's kind of a schematic representation of how we use Wave2Vec 2.0 with conformer architecture. So basic conformer architecture looks like this, where you have some input features. There's a layer that subsamples essentially the input spectrograms. There's some augmentation that you do up front when you're doing standard training. And then there's kind of like these a linear model here. A linear layer here, some dropouts applied, and the data is passed through a bunch of conformer blocks, and the final context vectors are obtained by some applying a projection block at the end. When you pre-train with Wave2Vec 2.0, what happens is that you generate these encoded features by the convolutional subsampling, and you mask part of the features that are passed into the rest of the network. And then there's some kind of an additional linear layer that you're targeting for that is not masked. And based on this masked information, you're trying to generate guess what the quantized, or what the masked features are, just based on the unmasked features. So it's literally trying to make the work for a dense spectrogram. So yeah. All right, so that's kind of the unsupervised method we'll be relying on. Then there's self-training. In self-training, we machine label the unlabeled data to help improve machine performance. So what we want to do is we want to train some kind of student model with the data labeled by a teacher, but we want the student to perform better than the teacher. So this sounds a little absurd, but actually people have made that work in image recognition. So there's this paper about noisy student training in 2020, where people were able to successfully apply this method by making the student actually be better than the teacher in many different ways. So first, they make the student have larger capacity than the teacher. They make the teacher produce labels from clean input, but then they augment the labeled data when training the student. So when the teacher is looking at the audio and generating the transcripts, it's looking at clean audio. It has a very easy time generating the transcripts, but when the student tries to guess the transcript, you're heavily augmenting the audio, so that the student is learning under harder conditions. And then once you train the student like that, you can set the student to the teacher, and you can kind of iterate. So this is kind of a schematic representation of what noisy student training looks like for speech. So we've done little tweaks to make it work kind of better for speech. So for example, given your data, again, like there are, we have a set of unlabeled data here and labeled data here. And this data set here is like some data set generated at some generation. So in the beginning, you just start with the labeled data. So you first train your student something, well, this model is your student right now. So the 0th model, the first model is a student of nothing. It's just student of the labeled data. But that student at generation G, when G is 0, it's just a teacher. Well, it's a student of nothing. A student at generation G is trained with some augmentation with the data at generation G. But then that student is made better by fusing with the LM, given some kind of language model, and becomes a teacher. So this teacher is equipped not only with the data from the previous generation, but it also has some language model that's helping it when it's doing inference. Then this teacher is looking at cleaned unlabeled data and labeling that. And then we take the labeled data and then we kind of clean it, we filter it with respect to confidence, and then we kind of balance it so that the distribution matches closely to the target distribution we want. And then we mix it with labeled data to generate the new data that's to train the next generation student. So again, like kind of the philosophy of training in kind of harsh conditions here. And then, so as a student, you're always training in a harsh condition, but as a teacher, you're doing inference in an easy condition. This is kind of the mechanism how the student gets better than the teacher. All right, so these are kind of the two semi-supervised learning methods that we employ. So given like all these developments, right? Like we're in a good position to use like a giant amount of data. So the natural question we asked, so I think this was work started a couple of years ago. We want to know how to leverage very large amounts of unlabeled data. And it's very natural to ask, can we make giant speech models that can perform well on a wide range of speech tasks with only a small amount of labeled data? So, so at the time, you know, these large language models like GPT and Lambda were all being trained and being put out into the ether. And we were kind of trying to do a similar thing in the space of the ASR. So essentially in this work, what we did was we were able to utilize a giant amount of unlabeled data, close to 1 million hours of audio, and use these giant models. Well, these are small compared to the giant language models that are in the market right now, but still these were, this is a pretty big model. So we utilized an 8 billion parameter model. And we kind of targeted a wide range of tasks spanning kind of multiple domains, multiple data set sizes spanning like 10 hours to tens of thousands of hours. And then we also we were able to show that these models, these giant pre-trained models can be very good for non-semantic tasks, and not just semantic tasks like ASR. So here's kind of the money shot of the paper that kind of summarizes the main takeaways. So just to kind of give you an overview, what we did was one task, we kind of first zeroed in on a very big task, on a labeled ASR task that had close to 30,000 hours of data, which is very big, right? Like you would imagine it doesn't really, it's not really like semi-supervised learning with like unlabeled data might not help a task that already has so much labeled data, right? But we focused on this this data set and kind of looked at smaller versions of it, right? Like a subsampled 100-hour data set and a subsampled 1,000-hour data set. And what we found was that scaling up is very good at improving the data efficiency. So the first thing, the first kind of like non-trivial result that we gained was that scaling up and doing lots of semi-supervised learning improves the task itself already. So you might think, hey, you know, say I train some kind of model on 30,000 hours of data, like, do I need to do, can this be made better? And the answer is yes, by utilizing giant amounts of data and training these giant models, you can still make a 30,000-hour task even better. But the other lesson was that we were able to improve data efficiency by a lot. So we were able to get kind of similar results to existing SOTA on this particular task by using 3% of the data. So semi-supervised learning and scaling up was really impressive in terms of like data efficiency, more so than just performance gain. So the other result, which you could argue is pretty predictable, is still that the scaling up pushes existing benchmarks, large or small, further. So if you look at the second kind of plot, we were able to, by using these scaled up models, just improve state of the art on various existing ASR benchmarks, large or small. So these benchmarks here are all public. They range from whatever, like hundreds, tens of hours to 100 hours, about 1,000 hours of audio. But these tasks are kind of industrial scale tasks that have tens of thousands of hours of quote unquote labeled data. And we were still able to improve that by a non-trivial amount by scaling up. And then the other like kind of surprise was that the representations produced by scaling up improved non-semantic tasks too. So we're all used to word array, so we view lower as better, but here the non-ASR tasks higher is better. So these are some accuracy measures on a bunch of non-semantic tasks. For example, speaker identification, or telling if speech is masked or not, sound classification, and so forth. By simply training a simple linear classifier on the representations that can be found inside the Zhang conformer, we were able to just beat existing like state-of-the-art numbers by just utilizing these representations. So that was like very surprising to us, actually. Yeah, are there any questions about this before I move on to kind of particulars of our results? Okay, cool. Yeah, so those are kind of the punchlines, but there were like various kind of lessons learned in the process. So let me kind of go over them. So these are kind of a subset of lessons that I found interesting. So one thing that was super interesting to us was that these models necessarily, as a model gets bigger, they necessarily have to be pre-trained, which was surprising to us. So here's an example of LibreSpeech that we all know and love. And this is the performance of a model trained on LibreSpeech, but as we make the model size bigger. So here's a 100 million parameter model. These are all conformers, 600 million parameter model and a billion parameter model. So if you just train on LibreSpeech from scratch, maybe we're not doing a great job at hyperparameter tuning, but actually in our defense, hyperparameter tuning cost as the model gets bigger is very expensive. So, we've tried to make this better by purely doing hyperparameter tuning, but still, the best numbers we were able to get on LibreSpeech by training from scratch actually gets worse as the model gets bigger. But once you pre-train the models, then the models behave normally. So the word error rate, as predicted, as models should, right? Like as the model is bigger, we want the performance to be better, and to make that to make that normal progression happen, we have to pre-train the models, at least to our, maybe there's some magical initialization or training scheme that we don't know about, but at least like this is what we've been able to do. So very interestingly, if you look here, if you go from 600 million to a billion, LibreSpeech training from scratch gets worse, but actually when you have a larger data set, it does get better. So this is kind of the voice search data set with 30,000 hours of data. And you actually see that as the model gets bigger, like it does like the performance mildly improves as you, so you might view this as really a classical overfitting problem, maybe. I think there's some debate, but this behavior kind of reverses here. But still, when you scale up to 8 billion parameters, actually, it's just very hard to make the model even train or converge in a reasonable way once you get to 8 billion parameters. So it seems like ASR tasks like RNNT or CPC kind of tasks are very, very hard to scale up, whereas the pre-training task seems to be easier. And maybe it's because the pre-training has more data. But we're able to pre-train those giant models successfully and make the performance better. The other thing we found is that, again, like semi-supervised learning is great for efficiency. So if you look here, we have two kind of models. So the first plot is the performance as we make the model data set bigger. And this is a single model. This is a 600 million parameter model. And the green line is just doing unsupervised training, and the blue line is doing unsupervised and self-supervised training. And we see like as the data set size gets smaller, the efficiency increases like vastly. So for like a tiny data set, by employing these SSL methods, we can improve the performance drastically when the labeled data set size is small. And as you see, as the labeled data set size gets bigger, the effects of scaling up become smaller, right? So down here, you're able to, as you make the model bigger, the improvement is like visible. Like this is a log scale graph, so the improvement is pretty significant. But when your data set size gets very, very big, the improvement from scaling up your model kind of diminishes. You have diminishing returns. But this is something you kind of like predict, but yeah. The other thing we found was that we see lots of cross-lingual benefits, especially at a low data set size. So Bo's going to talk a lot more about multilingual setups, but we find that in the low data set regime, we also see cross-lingual benefits. The other interesting thing we found was that, as I told you, right, like we were able to get very good non-semantic representations of the input audio inside the conformer. What we found was that so this is like the layer in which we find the good. This is the performance, the average accuracy measure of these non-semantic tasks based on the representation in the layer we got the representation from. So this blue line, for example, the conformer XL has like about 23 layers. So, this is like the first layer, and this is kind of the last layer. And we see that like kind of always the layers in the middle kind of do the best. So we want some representation deep inside the conformer model we want to use something deep inside the conformer model to give us kind of good results about the non-semantic content of the audio. So I found that interesting. So yeah, I think I'm right on time. So the advances in semi-supervised learning for speech recognition has opened kind of, we're all living in it now, a new era for ASR, where researchers are kind of now looking beyond just improving kind of public speech benchmarks. We're looking beyond that, I feel, and aspiring to train giant universal speech models that can do, many different things. So I think I'm very excited about this, and we'll talk about more kind of exciting, more recent developments by Bo. Bo and you will be presenting kind of more recent, more exciting results than this. Yeah, so I think that's my talk, and thank you for listening. Are there any questions or? So, I can't see or hear anybody, so.
May I ask a question?
Sure.
Hello, I'm Hongyi. I have a question. You show a very large self-supervised model with 8 billions of parameters. Oh, I know it's already very big, but does Google have the plan to train an even bigger self-supervised speech model? Because as you know, compared with those natural language processing model, usually they have today they can have more than 100 billions of parameter.
That's right.
Yeah, and I believe speech is more sophisticated than text, right? So we need an even bigger model. So are there any plan to train a bigger model, or are there something that stop us to train an even bigger model?
So I don't know how to answer that in a good way because I've been mostly so I think Bo or you can speak better about that because I actually don't know a good answer for that.
Yeah, I can
Yeah,
answer
yeah,
that.
sure.
So I think the question is for ASR or for general speech task.
I
So
think
I believe for ASR, like at least for now, from what we observe, like 8 billion models, things like already can achieve pretty good performance. So if you look at like a recently larger model trained by other giant group like OpenAI, Whisper is 2 billion, and Facebook published the XLR that is also 2 billion. So I think if you're just focusing on ASR task, let's say like speaker understanding task, classification task, I think I wouldn't say like scaling up the model further, there's no gain, but the gain gonna be like not as big as language model. However, if we talk about like speech generation task, I think for sure like we need a larger model. And like you mentioned, I think from the point of view like the complication of the signal, like text is part of a speech signal. So I do believe like for those tasks we need even larger model.
Yeah, thank you very much for your answer. Thank you.
Thanks to you.
And actually for speech, it's more challenging to scale up than text if you simply consider the redundancy information inside speech, and also the like sequence length is a very practical issue. Like you can easily train a text model over 2,000 tokens, but if you map those 2,000 tokens to speech, that's gonna like 10K tokens. And if you further map it back to the scaling law for the model size, it's actually the amount of a compute need for 8B model already similar to the 100B for text model. Yeah.
Yeah, thank you very much. This is a very good insight. So when we train an 8 billion model, the computation cost probably is already as big as 100 billion model on natural language processing. This is a very good insight. Thank you.
Hello?
Yep.
Yeah, this is Chen Li. Yes.
Hello. Yeah.
Yes. Hi. Thank you for a good tutorial. Now, my question is about some in many application domain, language modeling is actually more important than acoustic models. So I believe some companies, they would rather have their acoustic model not as big, but being able to integrate their own language models into the recognizer. So for what you have right now, it's a so-called general purpose recognition engine. but for many applications, this is not really good enough for specific domains. So in this particular setup, is there a way you can also integrate your own language model into such a setting?
Yeah, so I think that's a very, very good question. Essentially, you can mix and match the particular component we kind of focused on, right? Like today we focused a lot on the encoder, and
Yes.
you can view that as trying to make a very good acoustic representation of audio data.
Yes.
And you can kind of view it as a component of a much bigger system in that way. And there can be various ideas that expand upon that point, which I think like a lot of other people have demonstrated. I think like you and Bo can like as we go on, like this paper was from a year ago, so we're kind of like at like kind of a beginning point of like scaling up these models. But I think you and Bo can like their tutorials can like address like a little bit more of what you're thinking about. But I agree. Like I think this the like in a more modern viewing, by modern I mean like a lot changed over the year. You can view this as generating very good acoustic representations that can be further used by, say, like another big part of a big language model to do other things. So I think that perspective is out there right now, which wasn't clear to me, us at the time. Yeah.
Well,
that's a very good point. Yeah.
I think if you push in the direction of large general acoustic models, then of course we are talking about human performance, right? It's human is very good in general purpose speech recognition, but not always. For some topics they are not as familiar with human beings. They have to adapt to the conditions of speakers and speaking environments and so on and so forth. So we will have to deal with adaptation later on for such big models. And I believe that's, some of the applications Bo and Yu will follow up with. But I believe, yes, this kind of adaptation or transfer learning actually is more important in many practical settings.
I think that's a very good point. And I think that's also demonstrated by the large language model research, right? So like all the juice now, like people kind of think pre-training solved, and now like all the juice, all the kind of interesting stuff comes from fine-tuning those language models for specific purposes and coming up with smart ways of utilizing something like that. So I agree with you. I think that's a very yeah, I think that's a very insightful comment. Thank you.
And thank you.
Well, I guess if there aren't any more questions, I just do we have a break, or are we going to move over to use?
I think maybe let's move to the next one. Sorry, I have one.
Cool.
I think just to give it a time, like we don't want to drag it too late for the session, so
Yeah.
we'll keep to the next one. I mean, if there are like a time, we'll have a break after the second one. Thanks, Daniel.
Cool.
Thanks to the people asking the question there.
Thank you.
Let me bring up my screen. Do we have my screen? I don't think so, right?
No, I can't see it.
Yeah. Oh, I have some problem here. Let's see.
I don't know who has the control. Maybe Daniel
yeah.
has to release the control to you.
Yeah, I kind of stopped sharing, so it should
Oh,
be
okay.
fine.
Okay.
Yeah.
Okay.
Because oh, I think I cannot put it. Let me see this one.
Daniel, another way is that you control the slides you present again.
Yeah, if I cannot do that.
Oh, well, okay. So there's a little. Can you send me your slides?
Okay, let me send you the link.
Actually,
yeah. Just send to the chat. Thanks for that.
oh no, this is my. This is not my.
Oh. Your personal one?
Yeah, because yeah.
Okay, let me send from actually from the email.
Oh, actually, I can. Yeah, I think I can get it. Yeah.
Do you have the email there?
Yeah, I'll get it.
Good, thank you.
Yeah, hopefully.
Let's just I'll just reply them email again. So
I got it. I got it.
Okay,
so
cool.
it's
Yeah,
the PDF,
you.
right?
The PDF one, yeah. Thanks.
Yeah, I'll get it. Okay.
Okay, so well done. You pull up, have a pulling up the slides. Okay, there it is. Cool, thank you. So I think in previous section, as thanks to Daniel for laying the foundation, like we have been found a large interest in self-supervised learning and gigantic models there. So in this section, we actually try to look at towards another dimension. So basically the multilingual perspective. I think like just now also like properly mentioned about like the large models, how to reach like human capabilities for that. I think another aspect is like this model on some aspects actually maybe a little bit better. For example, for a human to learn a lot of language is hard, but maybe for I mean from our findings, like for a model to capture different language, actually you do not need a lot of like a lot of effort, a lot of challenges. That's like this kind of multilingual. Yeah, sorry, it's looking at. Let's go to the next slide. So basically in this session, we'll look at two problems. One is like scaling up. So how do you make such gigantic model to capture more language, to handle more language there? And the second part is like how do you further improve the quality of this kind of training stages? Because like you normally we do self-supervised learning and then do fine-tuning and additional on that maybe now student iterative learning there. And we'll try to see like can we make it further improvement on that. On top of that, so basically like the joint supervised training approach. Just okay, next one. So basically, just here is we put some reference. Basically, the talk of this part of talk is based on this 3 pieces of work. And next one, and so for the massive multilingual part, just to recap the problem, is that it's concerned about dealing with a larger number of the number of language and the amount of the data per each language. And it has some pretty good benefits in practice, like training and development and both like R&D part for, if you do monolingual, that scaling up is challenging, but if you can like the machine learning models to handle all the variations of language, and all you need to care about is just the downstream, how do you like route this model to different traffics there. And also like another perspective is like usually from the literature of the multilingual research, that the data sharing, data pooling across language, especially for low resource and tail language, that's the huge benefit. And if we can benefit using the high resource and learning from the data to encourage the sharing, that will be good in terms of like transfer learning and also like zero-shot capabilities for this large model. So basically, for this task, basically we want to build. We look at the entry model. So I mean, it's like most popular topic here right now in the field. So basically, we look at to build a single entry model for multiple language, and we want to ensure the quality is like comparable or even better compared to monolingual models. And meanwhile, like we have the benefit of production knowledge and simplicity. And so yeah, so basically like from previous Daniel's talk, we see like a pre-training improvement efficiency. We also want to further extend to the scale of the language. And next one. So I think just now in Daniel's talk, we also touch upon the capacity. So basically like the model size, we go up to from 600 million, 1 billion to 8 billion. And then another interesting point is like given the massive multilingual setup, what's the capacity problem? It's like do we need large models to capture that, and how in what kind of scale? So in that sense, we try to understand that based on a particular setup we present here. We look at the 66 to the 68 language. There is like around 600 million supervised data, and it's around 670,000 hours transcript data there. And the scale of the language varies quite a lot. In this figure is log scale. So basically the amount of supervised data actually differs quite a lot from the high resource and to the low resource one. So next one. And I think given that data scale, so to understand like this kind of scaling up, we manually split the language into 15 languages, 32 language, and 66. So basically 3 subsets, and some basic stats is over here. And also in previous plots, the color coded like different colors corresponding to different language, and it's like each one is like try to add more language. So we want to see like with this kind of procedure, like how does the model really needs like a large capacity or not. Next one. So basically like about observation, high level observation punchline here is just like a larger model capacity is needed if you want a good quality on more languages. And here we have some detailed results there. So we look at the first figures like on ENUS, how does this kind of scaling up the model size? Actually, the benefit is relatively small on the ENUS side. But if you look at on the B and C and D, so those are multilingual on 15 languages, 32 and 66 language. Definitely, like given a large model size, it improves the quality there. So overall, I mean, there are details in the paper, but here in terms of time, I just like to highlight is like basically we need large models to ensure the quality. So that is like the observation there. So can we do better on that? So basically, like yes, we can definitely push to have huge models, but are we at the best point that everything is well optimized or not? Are there any space we can further improve? So that's what we found in the next slide is like using a different learning schedule for to improve, given a fixed budget to improve quality. Next one. So basically, like we found in one of our studies, like using lifelong learning. So basically, we instead of like training everything from scratch, like if you have 60 language to train from scratch, or if you have like further 85. Oh, sorry, so, the further later study we also did 85, which is not updated to previous, but here we have some numbers there also. So basically, like if you continuously increase the number of language, one better way of like doing that is like you just reuse. Basically, you transfer the learned knowledge from the old model to the new set of language. That is better than you training everything from scratch. So basically, here we found that the best strategy is that you can start from 15 and to 32 and then 66 and further like even more like 85 also some languages. And from the table, the results, the two red box highlighted one is that basically you can train one model from random initialization, train from scratch. But if you compare to a learning from like a lifelong learning approach, it's definitely like worse compared to the reusing the existing checkpoint, which is like a transfer knowledge learned from previous model to the new setups there with new language, which is definitely much better compared to everything learning from scratch. So that's basically one observation we have found in this space of extending the model to more language coverage with a given fixed model capacity. Next one. Okay, so I think there, as mentioned, like so far, based on the self-supervised learning, usually there's multi-stage. So basically, you have self-supervised training, and then you have fine-tuning, and probably with noise students a few more iteration. And then from previous study in the multilingual perspectives, like if you want better quality, probably you need to iterate like a lifelong learning approach to gradually scale up. So those, I mean, there are multiple stages that there would be better. Can we simplify that? And from another perspective, actually, it's because like throughout all the fine-tuning part, one major concern is like the self-supervised learning knowledge maybe just be forgotten, because like it's a huge problem for neural networks, like catastrophic forgetting, because you are fine-tuning on a particular supervised data set. Then the previous self-supervised learn knowledge can just gradually lost throughout the training. So that's why we will look at the joint approach. Can we do joint training to maintain both the self-supervised knowledge and the supervised approach? So next one. And so just here, it's just a recap what Daniel had done. It's like in this particular setup, we look at conformal-based models, and this is just in the literature what the XLSR on the libre speech work, multilingual libre speech has done. Basically, you have feature encoder, you have content module with to vector module and the contrasting module here, and you have to learn a contrast loss. And next one. And then during the fine-tuning part, you add stick a decoder on top of the encoder, and then you optimize this kind of joint loss, this cross-entropy loss given the supervised paired data. Next one. And in our study, we found like we want to use the joint train the model with both supervised and unsupervised in a single stage instead of split into two stages. And in terms of unsupervised loss, right now we look at the contrast loss, the wave-to-back loss, and the wave-to-back birch mask language model loss on the audio perspective. And the supervised loss is basically we explored in our work is like the RNT supervised loss. Next one. So here is like a brief this architecture for the just joint unsupervised and supervised training approach. So basically, you have the feature encoder, which try to compress your feature into like hidden representations, and then you through a quantization module to learn this kind of context vector, and you have the wave-to-back loss, the contrast loss there in this figure, and next one. Next one, yeah, and then on top of the contrasted module, there is the based on wave-to-back loss. You have the ML loss. So basically, you tokenize the speech into the code book vectors, and then you try to use the basically borrowed from the language model birch experience, like we try to reconstruct the quantize the token there using a max language model loss there. And then on the right side, besides this kind of contrasted loss and the ML loss, there is like we stick a decoder, because the fine-tuning usually will have a decoder, and for the decoder we look at the RNT loss there. Sorry for this part, I went through pretty fast because like Daniel has presented the most of the detail that. But if anyone has the questions, feel free to pop up, and happy to explain more. And so back to, here, basically back to Josh. There's like in this kind of objective box, the dashed box. So we look at the three loss there: the unsupervised, the green color, the unsupervised, the contrasted loss, ML loss, and the red color RNT loss. That's the three loss we look at. And usually, like in the wave-to-back or wave-to-birch or wave-to-back two, there is to ensure the code book learned is that diverse enough that it's not collapsed into a single code vector. We have a diversity loss there. It's like on the right bottom right part of the figure. So basically, in the just we look at 4 losses there. It's like you have the contrast loss LC and the ML loss LM, and the diversity loss LD, and the loss of supervised loss, LS. So in our study, we look at we put just the 0.1 for the diversity loss, which is just more of a regularization term there, and that's the combination of the adjusted loss there. Next one. Okay, so for this investigation, we specifically look at, we're not on that large scale, the 60 or 80 language. We're looking at the public data set, which fastly to iterate. So we use this modeling or labor speech data set, and it stacks the 8 languages, including English, German, Dutch, Spanish, French, Portuguese, Italian, and Polish. And there are, it's a common standard in the literature. So we just put the stats table here. The interested people can take a look. I think like one emphasis I want to put here is basically if you look at the durations for the different languages, that's a pretty large gap from English to like the very low results like Polish or Portuguese, which is 100 hours, but for English it's like 44,000 hours of data. So large like diversity in terms of the amount of data. And next one. So this is like from literature. Usually for the monolingual and whatever approach you really want to look at, like how does this compare to the monolinguals? So basically, we want to make sure the monolingual model does not degrade. So this here we just reference the literature. What's the best monolingual model there? And next one. And this is like given the current standards. So if we do pre-train plus fine-tune, and the results we cite here is from the ISCSLP paper. Basically, like it's the model, the web-to-back model is pre-trained on the 53 languages of the total MLS instead of just the supervised part, and also including like common voice and Babel, all the kind of combination of the data. And because like for the pre-training part, you do not need the supervised Babel, so that's much easier to get more data there. And then we only fine-tune on the 8 MLS language here. And also just one note is like the fine-tuning is per language, so that in some sense usually is, I mean from experience usually is better than you do fine-tuning using a multilingual setup. And here basically we can see like if we do like a pre-train fine-tune, we can definitely get better over the monolingual systems, especially on the low resource language there. And the next one. And in our setup, it's like basically as we illustrated in the previous figure, like we use the just combine different supervised and self-supervised loss together. And there are a few like training stages schemas that we can explore. Like we have like a 4 loss component as we described before, and then we can explore like do single stage or 2 stage as a training. For there are a few configurations for single stage. We can do just without pre-training, just supervised loss only, or we can do supervised loss with web-to-back, the original web-to-back loss, or we do the plus the web-to-back merge, and also with a supervised loss. And then for the 2-stage training, we can do pre-training, we can do fine-tuning. That's 2-stage. Another alternative is like we are combining unsupervised and supervised loss. We can do just training and then do another round of fine-tuning. That's also possible. So basically, we want to explore all the possible combination of this. What's the best setup there? And next one. Here is like just a notion wise, like so basically we use LS to replace the RT loss as before, and here we combine the previous LC contrast loss and LM the max language model loss to just the LU to simplify it. So basically we put a weight for to combine the two the beta. Basically we weight the unsupervised loss during the just the fine tuning part. And we compare with the previous XLSR approach to see whether it just can bring better improvement or not. Next one. So here is like if we do beta equals 0, basically it's just like a not without unsupervised loss. Basically just training supervised with the web-to-back and web-to-back merge, and it already shows gain. So the benefit mainly comes like from the compared to XLSR is the web-to-merge part, because the XLSR is purely web-to-back instead of using web-to-back merge. So basically from our setup, the benefit even without joint supervised unsupervised, we have benefit that's just demonstrate the wave-to-back approach does bring additional benefits to the original wave-to-back part, the contrast loss alone. And we can see like overall on the average is like 8% versus the previous 10.6, the XLSR setup. So that's kind of the best in the literature at that time. And next, when we bring in the unsupervised loss, basically once we set the beta to be greater than 0, then we can see the results in the next slide. Here is basically like if we do the pre-training and unsupervised pre-training plus fine-tuning, that's the standard approach. Like, but given the same architecture, basically we have wave-to-back and wave-to-BERT loss there, and so we can see that it gives 7.8. And if we do like a pre-training plus just the fine-tuning, that's also 7.8. But if we do just directly from scratch, that actually give us the 7.3 on average. So that means like on this particular startup, we can like start from just the training. Like from when we combine unsupervised and supervised data together, for at least in this particular setup, there's not necessary to keep the unsupervised training as the first stage. We can just train from the just stage, and for the last one, we can further see is like if we do just the training first and then do another pure fine tuning, that it can give further improvement, which is the 6.9. That's the best result we get at that time. So that is basically was saying like instead of we do like a pre-training fine tuning, and we a better improvement is like we do joint training plus fine tuning that can improve the quality there. So that's the overall findings from this study. And next one. And we want to further understand the benefits. So what we do is we did more like an evaluation study. So basically we compare the baseline with just we can see like across language the ones actually is pretty consistent across language. And also if with without unsupervised loss, that's just the beta equals 0 and versus just, it's like with this kind of joint training, that's definitely better. And also, if you compare to other like a best model in the system in the literature report on this data set, the just setup is like also one's most actually on the low resource side, which like it makes sense because like the just bringing in this unsupervised loss, which is like seems the more general as well to the like tail languages. Basically, you try to capture more from the speech aspects instead of over-tuned unsupervised data there. Next one. So yeah, this is I think this is just emphasize like basically we can do this kind of just the training plus fine tuning. That just seems that's better. And if we look at the per language comparison, like it improves most actually both like high resource, low resource. Like in US, there is also some benefit with the just training, and on the low resource there is larger gains. So it's interesting to see the one data point we found is on the very tail resource, the Portuguese Polish, the PT and the PL, and different training schemas actually. It's to quite different quantize the tokens, and which can cause a large like discrepancy during training. And actually, we found like empirically just from scratch can better facilitate this low resource language to reduce word error. And that's just some findings on this particular site. And the next one. And this one is like another is like we can take the just the checkpoint because like with just we still have supervised loss, and that's give us a good indication like which checkpoint would be good. And then we find we can decide from the just training choose the best based on the like validation side, choose the best checkpoint and fine tune it with further supervised loss. That's the best. And if we look at the analysis on BE, the German and the Italian, IT and the Polish PL, this outperforms all the existing models very competitive on other languages. So this was saying like it's a good training strategy there. Next one. Yeah, this is just like what try to break down on the errors and per language and to a more clearly illustrate the one's answer is pretty consistent across different languages. Next one. And another is like because we have this kind of weighting factor into how much unsupervised you want to put into the picture, and we conducted some study. This parameter, hyperparameter beta does. I mean, the just training does kind of be sensitive to the beta, but it's not very like. I mean, it's we need to find the sweet point, but around the sweet point, it's not like you need to be very careful. Like if it's like change a little bit, is the quality changed a lot. Actually, it's pretty robust once you find the sweet point around the sweeping. And we run a few different values from the table. You can see that there are like whatever changes, but generally it's pretty good compared to like a two-stage like a pre-training plus fine-tuning approach there. And next one. And another thing actually we look at is like we compare to the two different attention, because like we are using conformer, which is based on transformer. There is like a attention module in the model setup. So we compared a local attention, global attention for the model. And from this plot, we can see like the global attention approach is definitely better across different language. So that's one data point. Like from when you like try to explore using the conformer or transformer-based approach, and some kind of application study we found will be useful here. And next one. And because we are using like a web-to-vec, there is the code book. And initially, like in the random XSR, like the web-to-vec fine-tuning, that usually doesn't fine-tune the code book. But in the just fine-tuning, because we have the unsupervised loss there, so the unsupervised loss on the like just the training part, it's got updated together with supervised loss, which affects the code book. So we wanted to see like whether the code books is the reason this kind of joint training is the better. Actually, I mean, from our application study, if we fix the codebook during just training, the result is pretty close to we update the codebook. So this implies like during just training, we can like fix the codebook. So basically, we can just rely on the codebook, learned before the pre-training part. But this depends like whether you start from pre-training model or not. Another is like even with just you can learn like a reasonable good codebook compared to two-stage training there. And next one. Yeah, this is similar. So basically, like if you try to adjust this kind of unsupervised versus supervised loss, they can learn different code books, but through the just training, actually, it doesn't affect that much for the downstream performance. And next one. I think another data point in terms of we are looking at the joint training is like because for the self-supervised training, there isn't a direct matrix connected to your downstream tasks. So it's hard to decide which point to be chosen during the pre-training part for your downstream task. And in this experiment, this application study, what we did is like we tried to choose different pre-training checkpoints and use it on the downstream fine-tuning. We do see like there is like a fluctuation like up and down in terms of quality. So basically like that was saying like if you do the two-stage training, there is still like you need some effort to a proper checkpoint. But with just the good thing is like because it has a supervised loss there, so you can just keep track of the supervised loss on your task. And to decide, I mean, to avoid this kind of like decision on which checkpoint to pick for your downstream task tuning before you know any quality there, and the quality after before the fine tuning. Yeah. Cool. Next one, I think this one is like a recent work from our group. Like we further extend the just to with Hydra, just the Hydra. So the motivation comes from this like there is a paper try to do this kind of layer-wise analysis, and they found in the web-to-vec models, the last 3 layer in the web-to-vec pre-trained model is more specialized to reconstruct master input. because like the self-supervised pre-training is to the contrast law to reconstruct, and that means the last 3 layers may not be good for your downstream discriminated task. So based on that motivation, what we adjust, modified our architecture is like we put the last 3 layer. We use two version to duplicate our last 3 layer. One for the web to back, bird loss, the unsupervised loss. Another is like it's the same structure but different parameters for the supervised loss, the RT loss. And from one of our production setups, the voice search and IME task, you can see if you compare to just versus just header, there is a clear benefit of separate the last 3 layer parameters for like supervised and unsupervised loss there. So given that, that's like most of the content of this section. Like next one, here just quickly conclusion. Basically, it's like we look at the 2 problems. First, like how do you scale up the language coverage for the large models? And we found that's like you need large model capacity if you want to maintain the quality across different language. And another way to address it to get a fixed budget is like you can try to benefit from the transfer learning from reuse in previous models, the lifelong learning approach. And another is like to address this kind of distract forgetting across multiple stages of training. We can combine the unsupervised and supervised loss together to ensure like you always have this unsupervised component even when you like update data fine-tuning on your downstream types to make sure the model doesn't forget what it learned before the self-supervised approach. And from the previous multilingual liberal speech, we found like if we do just like plus fine-tuning, that's the best. But in practice, like we don't always want to keep the large amount of unsupervised data around for your downstream task. So actually, a more recommended recipe, usually also like an internal external when published paper is like we still keep the self-supervised pre-training approach, but that is the first thing which trained like on large diverse audio only data. And those data is just on the to try to learn speech reprocessing, to try to reconstruct speech. And then like on your downstream tasks, you want do fine tuning. We do the kind of just based training. Basically, like we try to make sure the model doesn't forget what it learned from the self-supervised. Instead of like replace the self-supervised approach, but like we do the just as the second, like replace the fine tuning only approach using just. And lastly, it's like, I mean, once you do the just, you want to further increase the number of like language coverage for the model, kind of try to incrementally learning the model. Basically, reuse the existing model, like train them maybe on the small scale, and then small scale of data or small scale of language, and then try to progressively increase the language diversity, domain diversity to more domains, more language, and to avoid increase the capacity too much. But I think on another direction, as we discussed just now, like well, we definitely like want to explore like to push in the model capacity to be large. Like when do we really need to do that? And at what kind of stage like the model is like it's already really full capacity and we need to push it. But before that, I think there are spaces like we can push the quality without like increasing the model capacity. And I think in this section, we expand the language and we expand the kind of joint training. And in next section, you use talk, we'll discover that can we bring more modality, like especially on the text side? Can we bring more text training into this kind of big SSL, like this kind of self-supervised approach training? And before that, I think I think I take almost 45 minutes, 35 minutes. Okay, yeah. But we can have some questions here, and if there are questions before we move to, I mean, if we have time, we'll take a break. Otherwise, we can move to the next one.
Hi, Bo. I have a question. Yeah,
sure, yeah.
That's very impressive for this work for multilingual speech recognition. Just wondering, we have in practical, we have problem of code switch. Especially, it's very important in Singapore. We have multiracial culture, and everyone talk in more than one languages. So
Exactly.
code switch is a very important problem. I just wondering, just now you mentioned just what helps the low resource language speech recognition. I just wondering, you have any insight for code switch speech recognition?
Yeah, that's a question. That's definitely very like I mean, for us, one of the I mean, at present there are some motivation that we look at multilingual, massive multilingual. I didn't mention about the code switching because it doesn't cover any result there. But that's actually one of the biggest like motivation for us to also look at the multilingual for the code switching. I think yes, as you said, like in Singapore, that is a lot of code switching. Also, like in Europe, there's also a lot of code switching there. In terms of like production requirements, that's a huge need there. And from our research experiment, we found is like, for example, if you do multilingual, it itself is already a better starting point for code switching because like you already see a lot of data and the variation, and it's more robust compared to a single like a monolingual model there. And another thing is like in terms of just we do have some investigation in in our group, like we can like bring unsupervised like code switch data to try to make the model like using just the training to fine tuning your model to make it more like generalizable to this kind of acoustic difference for the code switching, because like for people like do code switch often, usually the acoustic variation is also slightly different from those kind of like a monoline speakers, and that can bring that aspect into it. And we do see some like in terms of water quality. Actually, we were like internally we are also in the same data set. I think that's like created from the Singapore service like Mandarin and English code switching data, and we do see some benefits. Like if we only bring like the same training data without a transcript into the picture through just the training, we do see some benefits on the testing the code switching. And another aspect actually, I think is from the text side, because the code switching, another is like the language usage, how you change it to which word is more often be changed to a different language. So injecting this code switching text into this kind of like multilingual model training is also useful. I think that part, I mean, Yu is going to talk about that. So basically, what he discussed in the next section. Well, we also like had some experiment with Joyce, which is Yu will talk about detail, and we see benefits there too.
Thank you. Thank you.
Thanks.
Paul?
Yep.
Now, so since we are talking about multilinguality,
yep.
So an unfair question would be, you know, I mean, different languages of course share quite a bit of similar acoustic phonetics properties. Yep. But how about text in terms yep. of language model? I mean, is that a viable approach to train pre-train a very large language model for, you know, multilingual problems, and then go from there to specific languages?
Yeah, that's another good point. It's like I think thanks for the question. Yeah, so basically in terms of multilingual, besides the acoustic, I think like usually I would take the opinion like language part is more complex than acoustic, because like I mean from previous like multilingual studies, like the number like we have IPA, so basically like the number of the acoustic realization the human can make, that's limited. But the language in terms of text, the language used is much more complex than the acoustic part. But I mean that's I mean debatable. But to me, actually one data point we have on our side is like we have been combined this like a massive multilingual ASR, the internal ASR, with large language model trained on large amount of like multilingual text, and that can further boost the quality, but actually by a pretty large margin. So basically, like even you train this engine, because the engine itself has a decoder. It's like a relatively weak language model, but it does capture some language model perspective. And we can see like on top of this engine, multilingual ASR models. If we bring this kind of large language model trained on multilingual text, that can even further improve the quality. So basically, this engine training here, I think a major part is because the parallel data we train for our multilingual ASR is, I mean, the amount of data is still limited compared to the large amount of text there. So that limits the capability of the decoder in our multilingual ASR capability on modern language. That's why it's like if we bring additional language model into the picture, that will bring our actual benefits there.
Thank you.
Thanks. Okay, I think we are like a pretty. Maybe we'll directly go to the next section here.
Okay, I'll try if I can share the screen. If not, maybe I still need Daniel's help. Daniel, if you're still here, maybe you can do that because it requires me restart my laptop.
Sure. Can you give me a second?
Yeah. Thank you.
Let me download it. Yeah.
Yeah, the reason is both of us we have to use Zoom in a personal laptop, which we were not very often to use. Yeah, we have internal to write Google for meetings, and those software are not allowed to install on cloud machine.
Okay, let me see if I can present. Let me see. You don't see it yet, right?
No, yeah.
Okay, let me see. You see it?
Oh yeah. Okay.
Okay. Cool.
Yeah. Okay, I'll just get started. So to continue with Bo's discussion, we also want to look at how can we adding more modality to the pre-trained speech encoder. So we call it a text injection. Next slide. So this talk is based on 3 work. One is the AmSlam, and the other is Metro. And at the end, we also talk about Joyce. Next. So the goal here is we want to build a pre-trained encoder that can encode both speech and text for many language, and we hope it can learn joint representations. So the pre-train allow us to leverage large amount of unlabeled speech and text. So what if we bring it together? That is kind of similar motivation like multilingual. So multilingual, you share representation and data across language, and you want it to improve the performance for low resource language. And for modality, it's just do the same, but it's cross modalities. So why we believe now is a good time to, let's say, there's many ways to do multimodality. So why we believe now is a good time to try a multimodality model for encoder. So the first and the most important things in my mind is we do see a convergence in neural network architectures, especially for different modalities. So for example, if you look at nowadays, the difference between a speech recognizer and a machine translation system is actually very, very close. Both use transformer-like architecture. And next few slides, I'll talk about pre-trained framework, and it also become very similar. And also pre-trained on unlabeled data, seeing a similar convergence, both modality like BERT and recent speech pre-training method all use mask language model strategies, which also makes it easier to learn a joint representation. Next slide. So just like a little bit more detail for the motivation. So why we do believe speech and text can help each other. Not this is kind of orthogonal for language model. You can always shift the domains. This is from the point of a language for middle resource language. The availability of speech data can be a bottleneck. So there is a lot of speech, but they're gonna have far more text. And this applies same for label and non-label data. So it would be nice if we can leverage text data for speech understanding tasks. And on the other hand, for some very low resource language, the situation might be changed. Like you might don't have a lot written script for those super low resource language, but you might able to find a lot more videos on the website. And we also hope like for those tasks, speech might be also help the text task. So ideally, we want this technology can help each other. This is a standard pre-trained encoder framework for text. It's called BERT. The basic idea is to mask the tokens and reconstruct the token. Next. And we do find that for speech, we can apply a very similar framework, and which is like we first discretize a feature, and then on top of those described feature, we apply the similar mask language model laws, and it can get like a very good performance on public benchmark. I didn't list here, but recently we have a paper early this year. It find like you even don't need to learn the discretized representation. You can simply just do a random projection. Let's say you random project a continuous feature to a codebook, and we still can get state-of-the-art result on many published benchmark. So this makes the speech pre-training and text pre-training almost identical. Like conformer is very similar to transformer, and both use mask language model laws. The only difference is quantize the feature and get the discretized target. Next slide. And for pair data, one popular thing in text side is it's called like a TLM. That's basically you concatenate the pair data for machine translation, and you mask it and reconstruct it. It's also get a pretty good performance. Next slide. And for speech and text pair, you can do similar things. You concatenate the feature and reconstruct both speech and text. And another way to align speech and task is the next slide. Is CTC. So basically, given speech, and you use dynamic programming to decide what's its output for the CTC loss. So why not we just like bring everything together? Like it shares the same architecture, it shares this very similar loss. So let's just like train a single encoder. It uses both unsupervised speech and unsupervised text with those joint loss. Next slide. So this is an overview for the multilingual encoder with speech and text framework. So give speech and text. Like speech, we have a couple layer to convert to the speech embedding, and then we send both speech and text embedding to a shared encoder. If it's a speech, we use Wave2Vec BERT ML loss to reconstruct it, and if it's text, we just use standard BERT loss. And for the pair data, we apply both CDC and TLM to make speech and text aligned. And we just like throw many data and scaling up this model and see what are going to happen for this pre-training framework. Next slide. So if you zoom in a little bit for this training framework, so for the bottom layer for text, we just use character embedding, or we can also use like a word piece model. It's just like whatever the basic unit you select for text. And for speech, we use a couple convolution layer to do 4 times length reduction, which would make the length of the speech and text more close, but it's still like it's not a completely aligned. Next slide. And for the supervised CTC loss, and for the supervised loss, this is like you have 2 modality. So you want those 2 modality aligned, and we also assume here we always have small amount of supervised data. So one way is using CTC. We just like map the speech to text directly. And we also tried the TLM loss. Basically, we concat speech and text and reconstruct it. Next slide. So the task we target here, basically including, because now like this model can accept both speech and text. So it will be interesting to not just look at the ASR. We also interested like what about a speech to X task? Like, so for example, for multilingual speech understanding, we looking at the performance on speech translation, speech classification, and speech recognition. And we also curious about what is the performance on multilingual text understanding, for example, translation and classification. And we will always compare to a speech only baseline. Next slide. So for the multilingual speech translation, we do the we benchmark on CoVoS 2. That is CoVoS 2 many to English speech translation task. That's basically you have many different language of speech and you translate to English text. So there are 21 source language. The amount of the pair data is actually quite small compared to machine translation. So for example, the this is some like just like some example. And for fine tuning, we use we added another 6-layer transformer decoder. So compared to the size of the encoder, the decoder size is quite small. So this can tell us how powerful of those pre-trained encoder. We just like simply mix all the language together. There's no tricks for like how to upweight the low resource or like how to sample those language. Next slide. We use this XLSR from Facebook. That's basically as a baseline. So they basically pre-train a large a 2 billion parameter large encoder on many public speech data set. And for the decoder, they also pre-train it on the text, and then they fine-tune both this encoder and decoder model. So our pre-trained data is a subset of this set because some of the data we are not allowed to use. You can see, so first we look at a smaller model, so we can ignore this larger one. We will have result for this 2B benchmark in the later slides. So you can see if we just like throw in all those data and we fine tune this joint training encoder and fine tune the speech only encoder, the performance is almost the same, like slightly better, like by 0.2 blue, which is almost like in the noise ratio. Next slide. So however, one big advantage of this joint pre-trained encoder is now you can easily use empty data in this framework, because now your encoder can take both speech and text modality. So during fine tuning, so this is actually one disadvantage of an end-to-end model. So if you train an end-to-end speech translation model, you can only use the pair data. It's hard to use a large amount of pair text data. So by doing this speech plus text pre-training, we actually can easily adding empty data to this joint framework. So basically during fine tuning, if it's speech data, then it's fine tune both encoder and decoder. If it's empty data, the encoder is shared. So you just throw in the text and you still can train the encoder and text and decoder part. Compared to speech only model, you can also do that, but you have to separately pre-train the decoder and the encoder. Next slide. We can see after adding those paired empty data, this 600 million parameter model actually perform a lot better. And for speech only, there's like a 0.6 blue improvement. However, for this joint pre-trained encoder, there's like more than 2 blue improvement, which is significant. That means like with this pre-trained encoder, we can easily utilize text information for this speech translation task. Next slide. And if we further scale up this model, because now you throw in more data, and more data typically means need more model capacity. So it's not surprised like by scaling up this model, we can do a lot better than the smaller model or speech-only model and all previous published like similar size of the model. Next slide. Next, we also look at the speech classification task. So what we do is we take, so we tested for spoken intent classification and also the Flores language ID task. So note that like we can see much more different language of text compared to speech in this setup. So that's very interesting to see how this model works on language identification. So our fine-tune pipeline is quite simple. So we just took the output from the MSLAM encoder and do max pooling on top of that, and then feed to a classification layer. Next slide. So we can see for both tasks, it's significantly better than speech-only baseline. For the lang ID task, the gain is larger, and it's also like benefit more by scaling up the model. Next slide. And now let's look at it back for the ASR task. So can those text data, so basically when we throw in more text data, how it affect the ASR performance? I didn't compare it with language model fusion in this presentation, but you can find all the language model fusion result on the paper if you are interested. So we benchmarked it on 3 different corpus. One is Vox Populi, 14 language, MLS. We use a 10-hour condition. This is 8 language. And the other is a Babel, which is from the AirPod challenge. So this more challenge data set compared to others. And we fine-tune it with a 2-layer LSTM anti-transducer, and there's no language model fusion. Next slide. As we can see by this is interesting. Like if we only look at speech only, so if we force the model has same capacity, speech only and speech plus text, there's almost no gains for ASR benchmark. However, like if we scaling up, we can see more improvement. Next slide. So at this stage, our goal was not to improve text modeling. However, like looking, so for example, the whole model is built on conformer, not a transformer. Conformer is particularly good for speech task because it encourages locality information inside the encoder. But it's still interesting to see how well it works for text classification. So we use XNLI as benchmark. It's a cross-lingual natural language inference task, including a couple of different setup. Next slide. So you can see the result was not as good as speech. So for example, if we compare to a small, it's actually not small. If we compare with the state-of-the-art MT5 benchmark, you can see our 600 million parameter model is worse than the similar size text-only model. But the good news is if we scaling up the model, the gap become much smaller. So the conclusion here is it's still like comparable, but it still means like this model needs more capacity to capture both speech and text information. Next slide. So as a summary, so we present a good massive multilingual speech plus text pre-training encoder, and it's particularly good for speech translation task, and it also performs strongly on speech classification, speech recognition, and text classification. As I mentioned in the result section, so if we limited the power, the capacity of the model, it's actually still slightly behind the ASR task. So how can we improve that? Next slide. One most obvious thing is, can we match the 2 modality better? So right now the modality matching is rely on CDC loss or TLM loss, and also like rely on sharing the same softmax for the mask language model building. However, like it's unknown, like so what most obvious thing is speech is much longer than text. So how can we like at least make the duration match? Inspired by the parallel tachytron work, basically we use learned duration model to upsample the text part and build a TTS system, we actually can do similar things here. That's basically we learn the duration model. And when we train this model for the text part, we first upsample it to make it similar as speech sequence. And then we can use RNT decoder to align both upsample text and the original text. We can also align speech and text. This is going to highly encourage the two modalities share in the same space. And it's also a unified framework for speech and text representation learning. Next slide. So this work is more ASR focused. So we compared on 3 standard ASR benchmark. The first one is in US, we use SpeechStew. That's basically 6 or 5 popular in US benchmark, including Switchboard, LibreSpeech, AMI, and etc. And Vox Populi, the multilingual benchmark. And at the end, we will also look at how if it can help speech to text translation. Next. So there's a lot of number, but I'll just talk about the conclusion. So basically, it's on par or better than MSLAM across many different domains. And if you look at the paper, we have some evidence. We have some virtualized figure basically showing, in this case, the two modality, the embedding of the two modality actually match better. So that's why it gives better performance. Similar stories for multilingual ASR. Next slide. You can see it improved the previous best result of 8.8 to 8.1 by adding text pre-training data. Next slide. And at the end, we also look at if all the benefit we presented before for MSLAM can still transfer to Mastral, especially for this COBOL translation task. As we can see, Mastral is much more parameter efficient than MSLAM. Just building a 600 million model, the result is already pretty close to MSLAM. And if we further adding speech translation and machine translation data to the pre-training task, this shares the same spirit as the JUST framework, which Bo just presented during pre-training stage. It's good also have some supervised signal, and then you do a second stage fine tune. This would match better. So you can see it's actually get a state of the art as a time when we publish the paper. Yeah. Next slide. So now we show adding to modality is helpful in some conditions. However, all of those work still require you have a large budget of computes. Smallest model we tried is 600 million parameter. So what if we do it on a much smaller model? Let's say on mobile, the smaller model for production. So this is motivate us to do this JOIST work. The basic motivation is similar, but we want to see how it works on a real product, in a real production setup. Next slide. Just a recap, what is the current prod model we use? This is published in last year. It's called Cascade encoder. Basically, you have a causal encoder at the bottom to do the streaming model, and you have more layer on the non-causal encoder that's do the second pass correction, and it's gonna output slow but give better accuracy. And the total model size is much smaller. It's a first pass is 50 million parameters, and the second pass is 100 million parameters. Next slide. And by adapt the joint training framework to this semi-streaming model, we actually only do the unsupervised training on the shared encoder part, because it can easily do the mask language model setup. Basically the unsupervised text part only goes through the cascade encoder part. For the causal one, we keep it as the same. So you can still get an output, streaming output through that encoder. Next slide. For loss computation, it's similar to Mastral. We have we still have the modality matching loss, and we still have the mask language model loss and RMT loss and unsupervised loss. Sorry, it's not similar to Mastral. I mean, it's similar to JAS. Like, this is basically when we train the model, we have both unsupervised loss and supervised loss. Next slide. One big difference compared to Mastral is we want to revisit the text modeling part, because upsample and having actual RMT loss is a little bit complicated for a product setup. So we can see if we can simplify if we can simplify this part. Next slide. The answer is yes. Like, we don't have to use a learned representation, at least for this setup. So we tried a bunch of like parameter free setup. One is we can do fixed repetitions. So basically we can repeating subword units by a fixed amount. This is similar to the paper from IBM in 2022, and it's very simple, and it works well showing that paper. The disadvantage is it does not model the actual distribution of each word, of each subword unit. So we also tried, next slide. We also tried a bunch of variations like random repetition. Next slides. And another way is we can first count the subword and build a Gaussian distribution, and we sample the length based on that distribution. All of those methods is motivated by, like, let's try to not rely on a learned duration model. Let's see if this simple approach works in this case. Next slide. Yeah, this is a basically we can also for the pair data, we can use false alignment information to obtain the duration model. This is like not train the duration model, but we use false align to get the duration. Next slide. And another benefit for ASR, which we didn't touch before, is so now, so for ASR, we not just do CE training, we also do the MTR training, basically, MWER training. Basically, it try to optimize the expected number of word rate. For a standard ASR framework, that's basically you give the hypothesis from, you give speech and you get the hypothesis word, and then you use this MWER loss on top of that. Within JOIST, we actually can compute MWER loss also for the unpaired text representation. You mask it and you get the text sequence, and you can also reuse the information from those unpaired texts. We are also curious about, this is actually similar to how we use machine translation data. That's a big advantage of those like joint representation network. Next slide. So here we train the model on since it's a prod model, it's like we have large amount of pair data for this setup. We are the most interested part we're curious about is can those models improve long tail test set? For example, so we choose like 5 different domain, which is all long tail word, including maps, news, play, and YouTube. Next slide. So you can see here the good news is like even with a fixed representation, actually already works pretty well for this setup. We get like a significant improvement among all of those like tail word test set. It's not so for the standard. So we didn't observe gain, also no loss for the like a standard benchmark. I think that is expected because we have large amount of training data. And the real benefit here is because you see this model seeing a lot more text data. So it's actually improved like those tail word for in US. Next slide. similar trends also hold for pre-train for streaming model. And if we compare it with Mastral, the result is actually comparable. So that means like we can use smaller model budget with a simpler training framework, but we can still get a good performance on those real world test set. Next slide. Lastly, we also looking at how it works for MTR training, MWER training, and you can see like by adding text information, we actually get a more improvement for MWER training. This is basically if you compare like a standard metric for on those tail word, it gives you something, but not as big as this under this like multimodality pre-train framework. Next slide. Yeah, I think I was just about the time. So a short conclusion is we do believe text injection is useful. We won't claim this is the best way to inject text information so far. Like there's many other way to injecting text information, and there are also other very good paper on this field. But yeah, I think this is I think now it's a time to bring two modality together and let them help each other. And the second bullet point we want to make is we do believe how to matching the two modality are important. And in the future, I think so now we are mostly focusing on how to bring the modality together for encoder. But you can see clearly a shift on the NLP world. Basically, they are shifting from pre-training encoder to a large pre-trained decoder part. So it's also interesting to see for speech, what is the best framework? Is that a unified framework for both encoder and decoder, or some new proposed approach? Yeah, definitely we want looking for a single efficient model for both speech and text model, and how to also make this model give good performance on text side is also very interesting. Like right now we can only see comparable for the text corpus. We didn't really see this model improve some standard text benchmark through like speech information. One obvious direction is like for pronunciation learning. I think actually I didn't show it today. It's actually showing some improvement, because when you do pronunciation learning, you do need like speech information and text information. Yeah, I think that's all I have. And I think we can have a couple minutes for question that can go for either me, Bo, and Daniel. Yeah, thank you.
Guess everything was super clear. Not a lot of questions.
Yeah.
I have a question here.
Sure.
Hello,
Yeah.
can everyone hear me? And Hongyi. My question is, now those text injection model, I think until now, some pair data is still needed to train this kind of text injection model, right? Are there any effort try to remove the need of pair data here? Thank you. This is my question.
So on our side, like we always looking for like a practical setup. So we always assume. So there's this. So for example, in the setup, we have some language we don't have a pair data, but we always assume there's a small amount of, at least like for in US, we always have some pair data to align the two modality. Yeah, I think
I see.
I think it's a very interesting, like if we remove all the supervised signal, and how can we still maybe one direction is Facebook, the zero resource ASR paper, but if I remember correctly, in their setup they still need a lexicon.
Yes,
something
they need a lexicon.
Yeah. This is my personal view, is like for many low resource language, like having a lexicon is even harder than like getting a lexicon is sometimes it's also not easy. So I think if we can do such thing like without any supervised signal, it's gonna be very challenging and also interesting. Yeah.
I see. Thank you very much for the answer. I have a follow-up question. Then in this kind of text injection model, what is in your point of view, based on your experience, what is the minimum pair data that is required to get this kind of text and speech alignment model work?
We find like we find, so in our setup we find 10 hours good enough, but we didn't like try 1 hour. So I have some experience on TTS. Let's say if the so far what I find is the biggest advantage of having pair data is to make the speech and text easier to like match with each other. And if we take the duration-based model approach, I think it needs about like 1 hour to match the modality. Yeah.
I see. Thank you very much for providing the insight. Thank you.
Okay, if no more question, we can take 3 minutes back.
Cool.
Sounds good.
Yeah.
Great.
And thank you
Thanks.
everyone for attending the talk. Yeah.
Thanks, everyone.
Thank you.
Bye.
Bye-bye.